Okay, so in this video, we're going to be talking about Le Chatelier's principle, which is a fancy way of saying simply this. If a reaction isn't at equilibrium, it'll do everything it can to get back to equilibrium. Another way of saying this is slap, slap back, which is not a really godly principle, but it's kind of what happens in every reaction. So whatever you do to a reaction, the reaction will try and do the opposite to get back to equilibrium. So let's take a look here. And there's some basic ideas here. Instead of saying that we're going to try and change the system, we're going to say this: when a system is at equilibrium, it's placed under stress. That's a fancy way of saying, hey, we're messing with the equilibrium. It will shift to relieve that stress. So what that means is that typically at equilibrium, you have the forward reaction and reverse reaction are going exactly the same rate, right? You're at equilibrium, dynamic equilibrium. If you mess with the equilibrium, either one will start going more quickly or the other will start going more quickly to get you back to the equilibrium K value that you should be at. So what are some of the things that we can do to stress our equilibrium? Well, we can change concentrations. That's the delta symbol for change. Or we can change the pressures. And that's usually a matter of pressure. I've spelled that backwards. That's usually a matter of changing the atmospheres or changing the volume. We'll get to that in a second. Or we can change the temperature, which has some other consequences, including impacting our K value. Stresses that don't do anything to us is adding an inert gas. That's like if you're dealing with a bunch of gases and you add an additional gas into a container, that will not impact your equilibrium in any way. Or if we add a catalyst. Now this is actually kind of a catalyst. I am spelling terribly today. Let's change that to an A. Now, the only way to change the value of an equilibrium constant is to change the temperature, which we just kind of discussed just a second ago. A catalyst, by the way, all it does is it speeds up a reaction to get to equilibrium, but it doesn't actually cause the equilibrium to do anything different than it normally would. So what I'm going to do is I'm going to use this example, N2 plus H2 goes to NH3, for all of our messings with stressors to our equilibrium. So first thing we're going to do is we're going to add and remove chemicals, and the chemicals are either N2, H2, or NH3. Now, before we go any farther, let's make sure we have a balanced equation, because even if we don't need to use the coefficients right this instant, we will need to a little bit later on. If I put a 2 right here and a 3 right here, I believe that we're balanced. Let me also point out a couple other things here to you. See this change in enthalpy for the reaction? That negative value, that tells us that we have an exothermic reaction, or heat is being released on the product side. And we'll get to that in a minute as well. So let's just take a look at this and think of it in terms of how do we get back to regular. So let's say I were to change the amount of NH3 and I were to add in a bunch more NH3, right? If I now add in a bunch more NH3, haven't I messed with the ratio? And remember, all of our ratios, aren't they the products over the reactants? If I've messed with that, and if I add in a bunch, and that's going to equal our K, right? If I add in a bunch of products, won't that impact our K? So the only way we can get that K back to what it was before is by shifting the reaction away from the side where we've added stuff to. And that'll mean that our products become reactants, and that'll lower our products while raising our reactants to get us back to a new K. Another way of thinking of it is this. Let's say I originally have this amount of reactant and this amount of product. That ratio is like 2 to 1, right? If I add in a bunch more of this, the ratio is no longer what it should be. So what's going to happen is it's going to shift this direction. And what will end up happening is that it'll get back to that same ratio as it was before. Now, if you notice something here, the amounts we had, originally we had this, right? The ratio was, let's say, 2 to 1. When I add in a bunch of this, now it's going to reset and still be 2 to 1. But in order for that to happen, we have to shift away from wherever we added. So adding chemicals in the reaction will shift the reaction away from that side of the reaction. Removing chemicals will shift the reaction towards. Now, another way of looking at that would be this. What if instead of removing NH3, what if instead of adding NH3, what if I took away NH3? So if I remove NH3, I kind of think of it like a suction. Like the NH3, you need more NH3 because to balance off our K, that means it's going to shift towards the NH3 to get us back to an equilibrium value. Hopefully that makes sense. Now, what if we add chemicals other than those that are in the reaction? So adding chemicals other than those in the reaction will have typically no effect on the equilibrium. So if I said, you know what, I'm going to add in a bunch of F2 into the container. So we have a container over here, and in that container we have N2 and H2 and we have NH3, and they're all happily at equilibrium with each other. If I added in a bunch of F2 in here, none of these things are going to interact with this F2, and this equilibrium right here, this equilibrium expression, which again, when we balance it, we have to put a 2 here and a 3 here. This equilibrium expression does not have F2 in it, so it's not going to be impacting it in any way. So the easiest way to think of it is we add something that's not involved in the reaction into the reaction container, it's not going to do anything. There are exceptions. If we add a chemical in here that will react with one of these things and remove it, then that can be the same as removing a chemical. So for example, if I added in a bunch of HCl, one of the things that I know is that HCl will react with NH3, and it will form NH4 plus and Cl minus, which we're not going to get into right now. But the end result is if I added HCl in here, which is not part of the original equilibrium, wouldn't that react with NH3 and in essence pull NH3 away? So you have to be careful because sometimes they'll throw you in something and you're like, oh yeah, that's not part of the equilibrium, it shouldn't do anything. But in reality, what that thing is doing is it's reacting with one of the things and it's either adding something to your equation, or in this case, wouldn't that be the same as pulling out some NH3 if we removed it to react with HCl, and that would cause it to shift in this direction. So however, sometimes adding a chemical will shift or remove or a chemical in the reaction, and thus taking that chemical away from the reaction. What I said before is probably a little bit better. Now, what happens if we deal with temperature? Now, think of it this way. Temperature only impacts wherever we have heat. And so what we can do is we can treat heat as either a reactant or a product depending on the sign of our change in enthalpy. Now notice right here, the sign is clearly, I'm going to make sure I have a better color in this case here. Our sign is clearly negative, right? And what that means is that we can treat our reaction as having heat on the product side. So if we treat heat as either being on the product or on the reactant side, temperature will do the same thing to heat as adding or removing something of a chemical will. So if I were to increase my temperature, right? So if I increase my temperature, since heat is on this side, it's the same as increasing the heat, and that would shift my reaction back towards this direction. If I were to do the opposite and I were to lower my heat, right? If I were to lower my temperature, not my heat, it'd be the same as removing heat, and the reaction would shift over here to fill it up. Now, the opposite would be true if we had an endothermic reaction. Now, we have an exothermic reaction because we have a negative value right here, right? But let's say this had been a positive value, or I said endothermic. That would be the same as having heat on this side, and the same thing, we can treat this as a reactant or a product. Now, one of the things you have to be aware of is this, is that when we change the temperature, it will permanently impact our equilibrium. So the one thing that can actually change our equilibrium as well, it'll cause it to shift one way or another, but it will also change our equilibrium constant. So when heat is added to the system, the reaction will shift away from the side of the equation where energy is. For an exothermic reaction, increasing the temperature will shift the reaction to the left, and for an endothermic reaction, increasing the temperature will shift the reaction to the right. Now, lastly, pressure shifts. Now, this is the one that can be the trickiest here. So here's the idea. Whenever we do something to an equilibrium, stress it in some way, the equilibrium will try and do the opposite to get back to equilibrium. So If I were to tell you that I raise the pressure on my reaction, the reaction will try and do what? We'll try and lower the pressure. Now, how do we change pressure in a reaction? Well, it depends on how many moles of gas we have on either side. So if I take a look at this example right here, we have 2 moles of gas on the product side, and we have 4 moles of gas on the reactant side. Now, if we take a look at these two here, clearly 4 moles of gas is greater than 2 moles of gas. And if I were to ask you which increases pressure more, 4 moles of a gas or 2 moles of a gas, wouldn't we all agree that 4 moles of a gas increases pressure more? So follow this. If I want to increase pressure, I will shift towards the reactant side because there's more moles of gas. That's if I want to increase pressure. If I want to decrease my pressure, right, then I will want to shift towards the product side because there's less moles of gas. So if I were to say in a problem, hey, when the pressure in the reaction is increased overall, right, in the container the reaction's in, the reaction will try and do the opposite and will try and lower the pressure. And in this case, it would be shifting to the side that has less moles of gas. So when it says when the pressure is increased, the reaction will shift towards the side of the reaction with the, now here's what's important. When pressure is increased, we're going to want to decrease the pressure. So it's going to shift to the side with less number of moles of gas. When the pressure is decreased, the reaction will shift towards the side of the reaction with more number of moles of gas. Now, here's the thing. They will not very often tell you that they're raising or lowering the pressure. What they'll often say is they're messing with the volume. Now, follow this. If I make my volume smaller, isn't the relationship, remember from PV equals nRT? Isn't the relationship between pressure and volume, isn't it inverse? So if I tell you that I'm increasing my volume, and that's typically what they'll say, isn't that another way of saying that they're lowering the pressure? And if they're lowering the pressure, what will the reaction want to do? Well, the reaction will want to do the opposite of that, and it will want to raise the pressure by shifting to the side with more moles of gas. So in this case, if I put this entire reaction in a container that was much, much bigger, right? A much bigger container, that would mean that the pressure is being lowered in the container. Because the pressure is being lowered in the container, the reaction will try and increase its pressure to get back to where it was before, and that would shift to the left-hand side. Does that kind of make sense? Now, the trickiest thing that they'll do is they'll sometimes say, hey, into this container where we have, and I'll make a new container. So in this container for the reaction above, we have N2, we have H2, and we have NH3. And they're all bouncing around in here. And they say, well, what if we added in I2 into here? What would happen to this reaction? And the answer is nothing. Shifts the equilibrium to no change. But wait a second, isn't this I going to increase the pressure in the container? Absolutely. There's going to be greater pressure because now you have one more gas acting along in here. But these gases independently, the N2, the H2, and the NH3, they do not interact in any way with the I2. And remember, one of the tenets of the ideal gas law is that gas particles essentially ignore every other gas particle that they're around. So unless the I2 is specifically reacting with the N2, the H2, or the NH3, any of those things, what's going to end up happening ultimately is that those three things are not going to interact with it, and it's not going to mess with the pressure in that system. So be really careful because they'll word it like the pressure in the container is increased by adding I2. What direction does the equilibrium shift? Yes, I2 would increase the pressure overall in the container, but because these three things here do not have any interaction with the I2, and they'll create the same amount of pressure that they did before interacting with the walls of the container, the overall reaction will not shift in any direction. And then adding a catalyst will shift the equilibrium to no change as well. We definitely are going to do some more practice problems, but let's take a look at this really, really quickly. I want to give you a minute here just to look at this. I want you to try it on your own, and then I'll come back and I'll walk you through it. Okay, let's try this together. If we remove H2O, that's removing this. Wouldn't it cause the reaction to shift to the left? What if the temperature is increased? Now, this is a tricky one here because we need to know whether or not this reaction is exothermic or endothermic. So if this reaction is exothermic, that means that we'd have heat on this side, and if I increase the temperature, wouldn't it shift in this direction right here? I'm going to pretend this is exothermic because I don't know off the top of my head if it is or isn't. Um, yeah. If helium is added, this is inert gas, it's not going to do anything. If CO is removed, we're moving on this side, it's going to shift this way. The volume of the container is tripled. Now watch, if I increase the volume, right, won't that mean that my pressure will go down? And if my pressure goes down, won't the reaction want to raise the pressure? In order to raise the pressure, we're going to shift to the side that has more moles of gas. And on this side, we have 4 moles of gas. On this side, we have 2 moles of gas. So the reaction is going to want to shift in this direction. So hopefully this has helped, and I will see you in the next video.